Hello and welcome. Today, we are diving deep into the very stuff our universe is made of. We're going on an incredible journey to understand matter itself. So let's start with a little riddle. What do a hard, glittering diamond, the massive, flowing ocean, and the invisible air you're breathing right now all have in common? I mean, they seem totally different, don't they? But believe it or not, they share one fundamental, incredible secret, and we're about to uncover it together. The answer, of course, is that they're all made of matter. But what does that really mean? Well, in this first part, we're going to unpack the building blocks of, well, everything. Okay, so what is matter? The textbook definition is pretty simple. It's anything that has mass, which is just the amount of stuff in it, and occupies space, meaning it has volume. You know, from the biggest star you can imagine down to a tiny grain of sand, it's all matter. But here's where it gets really cool. No matter what it is, a rock, water, air, you name it, it's all made of these impossibly tiny particles. And here's the kicker. These little particles are never still. They're always in motion, vibrating, bouncing, and zipping around. That constant motion, that energy, is the key to, well, everything we're about to talk about. Right, so that constant movement is what gives matter its different faces, or what scientists call states. And to make this super clear, we're going to follow a very familiar friend on its journey, water. First up, we've got the solid state. Think of an ice cube. Inside that ice cube, the water particles are packed together in this really tight, organized way. It's like a dance floor that is so jammed with people that nobody can actually move, you can just kind of vibrate in your spot. And that's exactly why ice has a fixed shape and a fixed volume. Now, let's add a little energy. Let's heat things up. That ice melts into liquid water. In the liquid state, those particles have enough energy to break free from their rigid spots. They're still really close, but now they can slide and tumble past each other. It's less like a packed dance floor and more like a party where people can walk around and mingle. This is why liquid water flows and takes the shape of whatever glass or bottle you pour it into. And if we crank up the energy even more, we get the gaseous state, steam. Now, the particles have so much energy that they just completely break away from each other. They're super far apart, zipping around like crazy in all directions. Imagine them like kids just let loose in a giant open field. And that's why a gas will expand to fill any space you give it, no matter how big. So let's just quickly put that all side by side. As you can see, solids have a definite shape and volume. Liquids, they keep their volume but take the shape of their container. And gases, they're totally free with no definite shape or volume. But check out compressibility. You can't really squeeze a solid or a liquid, right? But a gas, because those particles are so far apart, you can easily squish them together. It's a really key difference. Okay, so we've covered the what, the three basic states of matter. But now for the really fascinating part, the how. How does matter actually transform from solid to liquid to gas? The secret, in just one word, is energy. Let's go back to our friendly ice cube. When we add heat, we're giving its particles more energy, making them vibrate faster and faster. Once we hit 0 degrees Celsius, the melting point, something really weird happens. The particles have just enough energy to start breaking their bonds and moving around. But look at step 3. The temperature stops rising. It actually stays stuck at 0 until every single bit of ice has melted. So why? It's because all that extra energy you're adding isn't making the particles hotter. It's being used for one specific job, breaking down the solid structure. This hidden energy, the energy that's absorbed without a change in temperature, has a cool name, the latent heat of fusion. It's like a secret energy toll you have to pay to change from one state to the next. And this isn't just a one-off thing. The exact same process happens when you boil water. The temperature will climb up to 100 degrees Celsius, and then it'll just sit there, bubbling away until all the liquid has turned into steam. That energy payment to go from liquid to gas is called the latent heat of vaporization. Of course, boiling isn't the only way liquid turns into gas. Just think about a puddle drying up on a hot day. That's evaporation. It's a much slower process, and a few things can speed it up. A bigger puddle, which means more surface area, will dry faster. A hotter day, of course, helps a lot. And if it's not very humid out, the air can take more moisture so it evaporates faster. Oh, and a bit of wind really gets things moving too. And you know what? This simple idea explains something we've all felt. Why do we sweat? Well, as that sweat on your skin evaporates, it needs energy, that latent heat we just talked about, to turn into a gas. And where does it get that energy? It pulls heat directly from your body. It's basically your own personal built-in air conditioner. Pretty cool, huh? So we've got solids, liquids, and gases. That seems to cover just about everything. Or does it? Well, get ready, because things are about to get a little weird. We're now venturing beyond the big three, into the secret states of matter. So I've got to ask, do you really think that's the whole story? That everything in the entire universe is just a solid, a liquid, or gas? The answer is a huge no, not even close. So let me introduce you to the fourth state of matter, plasma. What happens if you just keep heating a gas to insane temperatures? Eventually, the particles get so energized that their electrons are literally ripped away, creating this supercharged, ionized gas. That's plasma. And while it might sound exotic, it is by far the most common state of matter in the universe. Our sun and all the stars you see at night, they're basically giant balls of plasma. But what if we go the other way? Not super hot, but super, super cold. There, we find a fifth state, the Bose-Einstein condensate, or BEC for short. This happens when you cool certain types of particles down to just a tiny fraction of a degree above absolute zero, the coldest possible temperature in the universe. At that point, the particles kind of lose their individuality and start acting together as one single giant superatom. And get this discovery was so profound, so absolutely mind-bending, that in 2001, the scientists who first managed to create a BEC in a lab were awarded the Nobel Prize in Physics. That's how big of a deal this is. So let's bring this all full circle. We started with a simple question, and we've gone from the ice in your drink all the way to the blazing heart of a star, and then to the coldest temperatures imaginable. And the big takeaway? It's all just matter. It's all just tiny particles, and the only thing that really separates them is how much energy they have and how they're moving. And that leaves us with one last really amazing thought. If the entire world, everything we see and touch, is just particles in different states of energy, it really makes you wonder, doesn't it? What other transformations, what other strange states, and what other incredible possibilities are still out there, just waiting for us to discover?